Okay. So the last thing that we need to cover in section 15.6 is the application of triple integrals defining moments and centers of mass. So in the section on double integrals, where we covered applications, we went over the formulas for finding the mass of a lamina and the center of mass of a lamina given a density function for that lamina. That's where double integrals are well suited, because we treat laminas like two-dimensional surfaces. But now we want to generalize that to three-dimensional solids, where in these formulas E is the solid that we want to find the center of mass and the total mass for. So by analogy to the definitions for mass and density function in the case of a lamina, we're going to suppose that we have a density function for our solid rho of x, y, z, and the mass would be just like in the case of a double integral. The mass of the solid E would be the triple integral of our density function over our solid E. We can go through a very similar derivation to show that that's how we would get our total mass. Similarly, we define the moments. So let me back that up for a second. In the case of a lamina, we talk about two different kinds of moments. We talk about a moment about the x-axis and a moment about the y-axis. And again, that's sort of a measure, in a sense, of the tendency of a lamina to rotate about either of those axes. In the case of three dimensions, we don't define moments relative to axes, we define them relative to coordinate planes. So for example, the moment that has this notation MYZ, this is the moment about the YZ plane now, instead of an axis. And notice we define it in a similar way to how we defined moments about axes in the case of two-dimensional lamina. The distance from any point to the YZ plane is given by the x coordinate of that point. And so this x here represents the distance from the point xyz to the yz plane. So we define the moment about the yz plane this way: triple integral over E of x times rho of xyz. And similar definitions for the moment about the xz plane, there would be a y here. Moment about the xy plane, there would be a z there. Just like in the case of the center of mass for a lamina, we defined the center of mass to be x bar, y bar, z bar, where each one of those comes from taking one of the moments and dividing it by the mass that we would have found in this step. Notice the moment that we use is the moment whose subscript does not include that value there. YZ here, so this would be an x here. Just a way of remembering that. So the derivation of all this would look so similar to what we did with laminas. We're not going to rework all of that from scratch. We're just going to say, here's the formulas. They're just a generalization of what we've already done. Let's try an example now. So we're going to look at finding the center of mass of a solid that has uniform density. Now, again, these problems don't have to have uniform density. The density can be a function that varies throughout the solid, but that complicates the integrand that we end up having to use in these formulas here. And most of the examples you're going to encounter in this section where we're finding center of mass are going to intentionally keep this function pretty simple. So for our case, we're going to say that the density at any point in this solid is 4, and we're not assigning any particular units to that for this. Okay, we want the center of mass of the solid E bounded by the cylinder z equals 1 minus y squared, and the planes x plus z equals 1, x equals 0, and z equals 0. And again, there's our density function. So let's start by sketching this region in 3 space. Okay. So we have x, y, and z there. Now, to begin with, the cylinder z equals 1 minus y squared is going to have a trace in the yz plane that looks like a parabola opening downward with a vertex at 0, 1. So that's going to be here. If this is 1, it's going to be a parabola that goes down like this. I'm going to have a -1 there and a +1 there. Okay, and it's a cylinder, so as x varies, this parabola is going to move along the x-axis, creating a cylinder. But then if we start to look at the planes that also bound this surface, we have x equals 0, which is the yz plane. So our trace right here is going to make up one of the faces of our solid because of x equals 0. Z equals 0 is the xy plane, so we're going to have a face of this solid that lies on the xy plane here. And then x plus z equals 1. I'm going to go into my xz plane and sketch the line x plus z equals 1. So if this is z and that's x, x plus z equals 1 is going to look like this. Okay, it's going to have an x-intercept and a z-intercept both at 1. So if I try to take that line and sketch it in the xz plane, here's the xz plane, and we should have an intercept at 1 on the z-axis and 1 on the x-axis. Let me join those 2 points. Okay, now remember, what I've sketched here is a line, not a plane. But because the description or the equation for this plane does not involve a y, then this line is free to move parallel to the y-axis, and it sweeps out a plane like this. Okay. So this is the plane that we're talking about right here. In addition to that, we have the cylinder, which is being cut off by that plane, which I'm going to attempt to draw. And it's going to cause this solid to be cut at kind of an angle, which you can kind of see the solid right here. Okay, so again, it's a parabolic cylinder that's been sliced by this plane here at kind of an angle. This is the solid that we're looking for the center of mass for. So in order to find that center of mass, we need to start by first finding just the mass itself, which we would use this formula for. In order to do this, though, we need to describe this region E. So here's E as a solid, either type 1, type 2, or type 3 solid. Now looking at this, because this is made up of a cylinder that's been cut by a plane, it makes the most sense to project this cylinder onto the YZ plane, which is going to give us that parabola. So I'm going to also sketch that parabola here in the YZ plane. So that's Z and that's Y. And that projection is going to be the plane region that we call D. Let's get a description of D down here. D is equal to the set of all x, no, sorry, not xy, it's yz. Got to be careful with that because we're in the yz plane here. The set of all yz such that, I'm going to describe this as a type 1 region in that plane. So I'm going to say y goes from -1 to 1. Z is bounded above by the function z equals 1 minus y squared, and bounded below by by y equals 0. So I'm going to say 0 z, and then what did we say? 1 minus y squared. Okay, so those are the bounds for our z. Now, let's come back up here. The only thing unaccounted for is x, if I want to give a description of the solid E. So x is bounded by the 2 surfaces, one showing up here in the yz plane, and the other showing up here in the plane x plus z equals 1. So looking at these 2 surfaces, what I need is a description of those. Excuse me. So, okay, so to get that description, let's think about what those 2 planes look like. The surface in the back here that we're bounded below, that comes from the plane x equals 0. So that's going to represent let's actually write our set E down here. E is the set of all x, y, z, such that x is bounded below by 0. Remember, that's the plane in the back here. And then it's bounded above by this plane right here. That's the plane x plus z equals 1. But I need a description of that plane where x has been isolated so I can see how x is affected by it. X in this case would equal 1 minus z if I solve that for x. So that's a description of this line, which is also a description of this plane, and that gives me an upper bound for my x. Okay, and I'm also going to write in the restrictions I have on my y and my z here. Y, again, goes from -1 to 1. Z goes from 0 to 1, 1 minus y squared. Okay, I didn't leave myself a whole lot of room on this page to write this problem out, so I'm going to do the work on another page here. Okay, so let's start by finding our mass. We're going to change the triple integral into an iterated integral, and it's going to look like this: -1 to 1, 0 to 1 minus y squared, 0 to 1 minus z of our density function, which is 4, dx, dz, dy. And again, if you're still getting used to how we set these integrals up, my reasoning for doing that is because we're looking at this solid as being projected into the yz plane, which is where we ended up getting the bounds on x right here. Where we project that plane and the limits of integration that we get as a result, that tells us what the innermost integral should look like. This means I'm integrating with respect to x on the inside. Then I would have to integrate with respect to z, because if you notice, it's bounded by functions of y. And I have to end by integrating with respect to y, since that's the only constant interval, the only interval where the endpoints are constant. So we can start by pulling the 4 out. So this is going to look like 4, integral from -1 to 1, 0 to 1 minus y squared, 0 to 1 minus z, dx, dz, dy. Now if I integrate dx, the antiderivative is just x, and the consequence using these limits of integration is I just get 1 minus z minus 0. So that's going to give me 4 times the integral from -1 to 1, integral from 0 to 1 minus y squared of 1 minus z, dz, dy. Okay, now we're going to integrate this with respect to z, so that's going to give me 4, integral from -1 to 1, integral from 0 to 1 minus y squared of z minus z squared over 2. Actually, I'm going to use square brackets there. And here we evaluate, oh, you know what, I made a mistake. I shouldn't have included this integral right here. Let's very sloppily scratch that out. These are the limits of integration here. That was my mistake. 0 to 1 minus y squared, that's what I'm looking for. Dy here. Okay, so we're going to substitute 1 minus y squared in for the z's. Plugging a 0 in doesn't do anything other than produce a 0, so I can just focus on that. -1 to 1. Okay, now if I were to have done that and simplified the result, I'm going to end up with, let's see, I get a 1/2 minus 1/2 y to the 4th. That's after all the simplification, dy. Now one thing I recommend doing here is utilizing the symmetry of this function. So you may notice that 1/2 minus 1/2 y to the 4th, this polynomial is an even function, and we're integrating over an interval that's symmetric about 0. Back in Calculus 2, when we encounter these, we say that, Calculus 1 in fact, we show that we can just integrate from 0 to 1 and double the result. So what I'm going to do is a couple of things in one. First, I'm going to factor a 1/2 out, which would change this to a 2. But then I'm going to multiply that by a 2, changing it back into a 4. And my limits of integration go from 0 to 1 now. And the integrand looks like 1 minus y to the 4th dy. The end result for this, I'm going to get a mass of 16/5. Okay, that's the mass of this solid. We're going to have to find the moments of this solid about each coordinate plane, but there's no time left in this video. We'll do that in the next one.